Oh, I
Before we
was
get
just.
started, maybe we should lay some ground rules about what equals means.
Oh yeah,
I think we should maybe say equal in area or something like
yeah,
that for parallelograms, because I'd like to keep equals actually meaning equals or congruent, uh, and not mix it up as Euclid appears to do. I find that deeply confusing. So yeah, if we
yeah.
can
I
agree to say
changed.
equal in area, then I think we'll be okay.
Yeah, I think I had the same thought. I changed them in my notes for to write equal in area because he actually applies the word equal to triangles as well later on to refer to triangles that are equal in area and not
Yeah,
necessarily
that's
equal
right.
in
Yeah,
size. So,
that's
there is.
where it
Yeah, so
crossed
there
my
is
line.
some ambiguity. Yeah, yeah, yeah. So yeah, so I think I agree with that. Otherwise otherwise is completely completely ambiguous. Okay, so yeah, so I think this proposition is essentially a corollary of the previous proposition 35. So this proposition says that parallelograms on equal. And I think here I can leave equal unadorned because we're talking about a side, the equal basis, and between the same parallel lines are equal in area. Parallel lines are equal in area. So recall the last proposition was almost exactly the same. It was two parallelograms on the same base. Actually, this essentially says they don't have to be the same base. They just have to be bases of equal length. So let's draw the diagram. I probably have. Well, I have to draw it here because it doesn't make sense to go to a new board just yet. So let's draw the diagram. I'm going to make it a little bit smaller. Maybe this is too small, but we'll see. So parallel lines. Uh, Start with some parallel lines. I'll draw some arrows to indicate they're parallel. And I'm going to have parallelograms on these parallel lines. Go back to line tool like this. So this is the first parallelogram. And I'll draw another parallelogram. I'm going to purposely make it a little bit wonky. So like this. Like that. All right, so these are parallelograms on parallel lines. I'll label the points A, B, C, D. That's the first one, and E, F, G, H being the second. And we're going to assume that B, C, and F, G are equal in length. So these two are equal, right? So I guess let I'm going to let AH and BG be parallel lines, and ABCD and EFGH be parallelograms with the side that's on the same line equal, so BC equal to FG. Okay, and so I guess the claim is that the areas of ABCD and EFGH are equal. And so the way we're going to do it, we're going to construct a parallelogram that kind of intersects these two. Yeah, so the proof is that we're going to construct a parallelogram by joining B and E. So I'm going to join B and did I not use the line tool again? If I don't use the line tool, I'm going to have to carefully erase this line.
Can't you do undo?
Where's the?
You
Oh
can't.
God! Yeah, you're right. Yeah, I
You can't.
can.
Can't. Oh
Oh,
yeah,
I
maybe.
got it.
Yeah.
Yes. Thanks, Dan. So now I'm on line two. I'm gonna draw a line BE and CH. So this thing is gonna be the common parallelogram that links these two. Recall last week that we had a proposition that said that parallelograms with the same base have equal areas, and now you can already see where this is going. We're gonna use the red parallelogram to apply last week's proposition. So we're gonna construct, wrong color. I'm gonna construct, as I just did, lines BE and CH, right? And so we get a parallelogram as shown. Since BC and FG are equal, hang on. Since BC and FG are equal, hang on, let me just read it. Doesn't make any sense. FG and EH equal.
You want BC equal to EH, then
Yeah. I think. Oh yeah. So I'm just getting there. So since BC and FG are equal, and FG and EH are equal, BC and EH are equal. Probably should say
so
why.
Second. Yeah, right.
Yeah, so FG and EH are equal. This is due to proposition 34. Remember that opposite sides of a parallelogram are equal. So that's the kind of information we need. Everything else is already kind of assumed. Oh yeah, well, BC and FG being equal are assumed. Okay, so we want to say that BC and EH are equal. So let's move on to the next board. So by proposition 33, the straight lines BE and CH BE and CH joining equal and parallel straight lines. And these are BC and EH, which we've shown to be equal. On the same side are parallel. Okay, hence EBCH is a parallelogram. I've forgotten that we actually have to prove this. Right, so yeah, we've constructed this shape with BC and EH, right? And we've just shown that because BC and EH are equal and BC and EH are actually parallel, then then the figure that we've drawn with the red lines BECH is actually a parallelogram. And so now we can finally use last week's proposition, which is 35. The area, I spelled area wrong. Oh, that was a big eraser. What did I erase? EBCH is right.
You can undo the eraser as well.
Oh yeah. Sorry, I keep forgetting. Thanks.
Well, it didn't used to be a feature, so it's reasonable to forget.
Oh, is that new? All right, nice.
Not new, but it wasn't always there.
So I think this is why I was erasing it, because I was trained to manually undo, right?
That's right, yeah.
Good to know. Areas of A, B, C, D, and E, F, G, H. Right. So EBCH is the common parallelogram that
Sorry,
shares
you
side.
you wrote
Oh, yeah.
EHGH.
Yes, that. Oh, undo. It's a EFGH, right? That's what I meant. All right. Cool. So since it shares a side with each. Not the best sentence, but EBCH shares a side with both ABCD and EFGH. Cool. And so 35 says that if parallelograms share a side, then they have the same areas. Yeah, cool. Okay, I think
Cool.
that's it.
All right. You want to detach and I'll attach.
Yes. Cool.
All right. Okay, so proposition 37 says that, so now we're going to use what we've proven about parallelograms to make similar statements about triangles. And essentially they're going, there's 3 or 4 of them, I guess, and they're going to follow by just chopping parallelograms into triangles and constructing parallelograms out of 2 copies of a triangle. And that trick will just basically be all we do. Triangles which are on the same base and in the same parallels are equal in area, not congruent necessarily. All right, so here's the picture. So I've got 2 parallel lines. We're going to prove a more general statement, but for the moment we have 2 triangles with the same base, which is BC, and their other vertex is on the line EF. Oh, I guess I haven't constructed those yet, so maybe I shouldn't draw them. So let's say AD. So this is another line parallel to BC. So the setup rather is that we have triangles ABC and DBC. And we want to prove that they have the same area. I quite like this proof. All right, so we know something about a similar question for parallelograms. So how are we going to construct parallelograms? Well, I have this line AC here, and I can move it over there. Now, moving a straight line is something we know how to do on the basis of it's proposition 31, I believe. Let me just check. Proposition 31 says, through a given point, draw a straight line parallel to a given straight line. That's not moving a finite straight line because it doesn't get the length correct, but we can apply an earlier proposition to do that. In the current situation, we don't have to invoke that because we can just extend the line AD. So I'll do that first and then see where that line meets it. So extend AD to a straight line. And by proposition 31, let EB be drawn parallel to AC, and FC, excuse me, parallel to BD. So I'm going to draw this as long as you like. Then I'm going to draw this line parallel to AC by proposition 31, and I'm going to call where that meets that line ADE, and then I don't need any more of that line. So I'll just not draw the extra bits that I won't need. So let's see. It's roughly... Okay, so these are the new things here. So this is E, and this here is F. Okay. First, let's observe that they are parallelograms. So EBCA and DBCF are parallelograms. But the definition we have for parallelograms is that they're two parallel lines, the sort of region bounded inside them. And that's how I've constructed these, right? So by construction, EA, which is in the same line as AD, is parallel to BC, and this is parallel to that, and so on. So these are parallelograms by construction. All right. Now the area of the former, so EBCA, is twice the area of the triangle ABC. We prove that in proposition 34. And similarly, the area of the latter, so the parallelogram DBCF, is twice that of the triangle DBC by the same proposition. But by, I guess this is proposition 35, we don't need the most general version. So those two parallelograms share a base, let's say BC, right? EBCA and DBCF share the base BC, so by proposition 35, they have the same area. Well, so we have one area, which is the common area of those two parallelograms, is both twice the area of ABC and also twice the area of DBC. And what Euclid writes at this point is, but the halves of equal things are equal to one another. That's not a common notion, and I don't think we have the ability to halve things necessarily. If we did, then we wouldn't have to prove we could bisect angles and bisect lines, right? So I think halving is not really a fundamental operation in Euclid. Doubling, on the other hand, is, because we can consider adding things. So really there's a statement here which needs to be justified from the common notions, which is that if you take a quantity and you double it, and it's equal to the double of some other quantity, those two quantities are equal. And that can be proven by proof by contradiction, assume one of them is larger than the other, and then when you double it, you'll get a strict inequality between their doubles by using the greater is larger than the part, and so on. So I think it's not really worth getting into the proof of that. It's an exercise, if you like. But yeah, that is something that in principle needs to be proven. Okay, but since we can invoke that, we can see that the area of ABC is equal to the area of DBC, and we're done.
Cool, that's a nice proof.
Okay. Yeah, I enjoyed that. I thought that was very, very nice. How are we doing for time?
Got like 5-6 minutes left. I don't know. Should we try to do another one, or maybe leave it? I don't know.
Yeah.
Let's see.
Proposition 38. Triangles which are on equal bases and in the same parallels are equal to one another. Yeah, I think maybe it's going to be a stretch to get it done in 5 minutes. Let's just leave it.
Yeah, all right, cool. We'll start with that next time. Your one was just short. It fit on the same on one board. That's cool.
Yeah, only just. If I had more board, I probably would have written something about the halves. But
Yeah.
So what have we got left in this book? Let's maybe take this opportunity to see where we're going.
Yeah, I thought
So
you said there were
proposition.
50 or so, like up to. Let me check.